All right, good morning, everyone. Happy Easter. It's Easter Sunday, and we are going to forge along here today and do section 6.6 on complex numbers, starting with our first objective, Objective A, which is to simplify square roots of negative numbers. So now we change it up a little bit and talk about the number, for example, the square root of negative a. So now we're going to be able to take the square root of a negative number where prior to this we said we weren't able to. So now we needed to develop something in mathematics to allow for the square root of negative numbers. And we also refer this to as imaginary numbers or the imaginary unit. Okay, so if I've got the square root of a negative number, the negative 1, I could say the square root of negative 1 will equal I, and I is the imaginary number. Okay, if I square I, if I go I to the second power, that's going to equal negative 1. So these two theories here, or facts I should say, they're not even theories, I could say is what we're going to be using a lot in this section, in this chapter perhaps. All right, so I equals a square root of negative 1, I squared equals negative 1. Okay, so what about it? So here I've got the square root of negative a, and so I could look at this as being the, let me move this up, I'm going to rewrite this to square root of negative 1 times a. All right, the square root of negative 1 is I, according to this. All right, so that part of it is going to be I. That's going to come out front. And then I'm left with the square root of a. Okay, and then I could say to justify this, our role here, if I took a square root of I times the square root of a, and I squared it like this, going backwards, then I could justify this by saying, what does this equal? I squared times a. I'm squaring the square root of a, which is a, and then I'm square rooting the I to give me I squared. And now what can I interpret from this? That I squared equals negative 1. That's what this statement is saying here. So if I squared equals negative 1 times a, so therefore negative 1 times a is negative a, which we started up here, taking the square root of negative a. All right, just a little justification issue there. Okay, now let's see what we got next. Okay, and here's what we got with example 1. All right, so no longer do we say the square root of a negative number is undefined. We say it's going to be, well, here I can see this is going to break down to be the square root of negative 1 times, extend this, 25. And then I'll break it down as to what I know. And what did we say earlier? That I equals, or I could say I squared equals negative 1, and therefore I would equal the square root of negative 1, taking the square root of both sides. I like to just keep this with me as my little guide for when I'm doing this problem here. All right, so I got the square root of negative 1. It's here. That's going to be I, and I is going to come out front. And then I can simply take, what's the square root of 25? That's a perfect square number, so it's going to be 5. So I'm going to write this up as 5i. I is a number, but I'm looking at this. This is a variable. Just for the sake of writing this up as 5i is the proper way of writing your answer. I5 looks just backwards to a lot of us. All right, B is kind of like the same concept. This is going to be 7i. Square root of 49 is 7. Square root of negative 1 is I. How about the square root of negative 12? Well, this is not a perfect square number, so I can take the 12, I'll do it here, break it down, and let's call it 4 times 3, and then I could say the square root of 4 is 2, with the 3 left inside, and then I've got that square root of negative 1 here, and the square root of negative 1 is I. So I'd write this up as 2 times I times the square root of 3. And D, square root of negative 17. Well, the square root of negative 1 times 17. Remember, I'm looking at it this way. The square root of negative 1 times 17. Okay, the square root of negative 1, that's the I. And the square root of 17 is the square root of 17. I can't factor 17 as happens to be a prime number, so I just leave it under the radical sign. Very nice. Okay, going on to objective B, we are going to simplify powers of I. Okay, powers of I. Simplify them. All right, so I've got a nice way of doing this that deviates slightly from what the textbook is telling us. Same concept. So let's see here. For powers of I, what I need when I'm simplifying powers of I is I need to know that I to the 0 power equals 1. I need to know that I to the first power equals I. I need to know I to the second power equals negative 1. And that I to the third power equals negative I. Okay, we know this ahead of time. Now, I to the third, how do I come up with negative I? And just so you know, it's going to be, let's see, I can break the I down to be I times I squared. That's I to the third. I squared equals negative 1. And I is I. So I times negative 1 equals negative I. Okay, so that's how we can determine that. Just FYI, for your information. Okay, so these are the main culprits here. Let me scratch that off for now. And these are the guys I want to keep handy to recall that when I need it. And now I'm going to show you some ways of going about doing this. Let's see, in our example 2, they have A, B, and C. So I've got I to the 30th power. And I have to simplify that. Okay, so let's see. Here are my 4 components. Notice I got 1, I to the 0, I to the first, I to the second, I to the third. If I went to I to the 4th, well, that would be negative 1 times negative 1. I squared times I squared, which equals positive 1, which I have over here with I to the 0. So this sequence of numbers will repeat itself for every 4 components, I'll call them, 4 factors. All right, so what I can do is I'm going to take that 4, that number 4, because there's these 4 components, and divide it into the exponent of 30. So I'm going to go 4 divided into 30. Okay, what do I get? So it goes in 7 times. 7 times 4 is 28. And then I've got a remainder of 2. And this is what I'm interested in now. I'm interested in the remainder, not the quotient. All right, so now I can get my answer by just putting the I and using the remainder as the exponent. So this becomes I squared, so therefore I to the 30th power is going to equal what I to the square is. And I to the square is here, which is -1. So I to the 30th power equals -1. My next number is I to the 11. I want to simplify that. So let's take the 11 divided by 4. And I'm going to have 4 goes into 11 2 times. 2 times 4 is 8. I subtract. 11 take away 8 is 3. So I've got I to the 3rd power. And I to the 3rd power, as we recalled, I'll just scoot it up here because you can keep this with you. I to the 3rd power equals -I. And therefore, I to the 11th power is -I. Like so. Okay. Last one, I to the 40th. I have to simplify that. If I simplify that, I'm going to have 40 divided by 4 is 10 times. 10 times 4 is 40. I subtract. I got a 0 remainder. So that means my answer is going to I to the 40th is going to be the same as I to the 0. And I to the 0 equals 1. And that's how you simplify powers of I. Division by 4. Okay, good. So I can take any power of I as large as I want. I to the, let's say the, I don't know, 151st power. And if I have to simplify that, what would it equal? Well, I'll take the 151, that's a 5, 151, and divide it by 4. Always dividing it by 4. 4 goes into 15 3 times. 3 times 4 is 12. Subtract 31. 4 goes into 31 7 times. 7 times 4 is 28. Subtract 31, take away 28 is 3. So my answer is going to be I cubed, the same as I cubed. So I to the 151 is going to equal I to the 3rd, which is going to equal -I. Easy as that. Hard part is remembering what to do. Division by 4. And you're using the remainder. All right, next up. Okay, next up is talking about complex numbers. Complex numbers. And what are they? Complex numbers is any number that can be put in the form a plus bi, where what? This is called the standard form for complex numbers, this a plus bi. The number a is called the real part of the complex number. The number b is called the imaginary part, because it's multiplied to I, and I is the square root of a negative number. All right, so every real number is a complex number. For example, 8 can be written as, so this is I've got a number, we're used to just calling it 8. 8's a number, but it's also a complex number, because I could write this 8 in a different form, in particular, 8 plus 0, I, where 0 times anything is 0. So this is in the a plus bi form, the complex form, written that this way, and then it equals 8, because 0 times I is 0. So it just goes right back to being 8, but I'm writing it in a complex form. All right, this is one example. There are more examples at the bottom of page 567 of your textbook if you'd like to delve into that. Okay, so let's see. What do they want us to do now? That's 567, 568. Equality for complex numbers. All right, so let's get into what they're asking us to do, and that would be of the form example 3. All right, here's example 3. We have find x and y if 3x plus 4i equals 12 minus 8yi. A little different form of an equation that we're accustomed to working with. However, it's basically the patterns that you're looking for that follow one problem to the next. So what happens here is the order that I want to write these equations out. I've got, notice that I have 3x plus 4i equals 12 minus 8yi. So I'm going to start off with the y. I'm solving for y first, because when I do, this 8y times I has an I in it, and so does this 4. So I'm going to take these as two pairings. I'm going to write this up as 4i equals negative 8yi. Okay, that's what I want to do. And now I want to solve for y, basically. All right, so I could take, let's see, I'm going to get y by itself, so I'm going to divide both sides here by negative 8i. And over here, negative 8i. What I do to one side, I do to the other. Okay, so I know the right side's going to equal y, and then the left side here, well, the i's cancel, and then I got 4 over negative 8, which is the same as negative 1/2. So there's my value for y. When we do the y's, what we want here, notice I have an I on the left side, I on the right side. I don't even have to write, I don't even have to bother with the i's, because they end up canceling out each and every time. You can, if you want, keep them. It really doesn't matter, as long as you isolate that y. Okay, so I got my answer for y. And next then, so I use the i's here for I and that negative 8yi. Then I'm just left with 3x equals 12. And solving for x, x equals 4. And there's the value for x that I want. So these two guys here are my solutions to that example 3. Okay, example 4 is next. Okay, in example 4, we've got this line up here again. All right, so I could look at this now, and I've got 7i equals this binomial times I, getting my i's together. So I'm going to do that first. 7i equals 2y minus 1 times I. Okay, again, I can see that the i's are just going to cancel each other out, so I'm not even going to worry about it. I'm just going to write it up as 7 equals 2y minus 1. Okay, and now I'm going to solve for y. Well, the parentheses aren't doing anything, so let me back out of there. And I'm going to solve for y. So I'm going to add 1 to both sides. And I've got 8 equals 2y. And if that's the case, I'm going to divide both sides by 2. So y will equal, what is that, 4. So y is 4 is one answer. And now in this equation here, I've used my I, so these are gone. And I've got what left? 4x minus 3 equals 5. 4x minus 3 equals 5. And I'm going to solve for x. So let's add 3 to both sides. I got 4x equals 8. So divide by 4 and x equals 2. And there you have it. My answer for example 4 is x equals 2 and y equals 4. All right, very nice. Okay, our next objective D is to add and subtract complex numbers. Okay, very easy, very nice to do. It's the same as adding and subtracting polynomials, where you're looking for like terms to be able to combine. And that's all there is to that subtracting part. I'll alert you of what to be aware of. So let's do some examples in example 5. Okay, here's our first example of adding and subtracting complex numbers. So here I've got 3 plus 4i plus 7 minus 6i. Well, because I'm adding, there's no changes that are going to be made, so I can just drop the parentheses. And it would be 3 plus 4i plus 7 minus 6i. Okay, now I can see better, and I can see that I'm going to combine my like terms. And my like terms are these constants of 3 and 7. That'll give me 10. And then how about 4i minus 6i? 4i minus 6i is negative 2i. And notice this answer is in the a plus bi form. So this is my solution for example 5a. B of example 5, now notice I'm subtracting. So just like with polynomials, I have to distribute the negative 1 going across. And I want to do that first. So I'm going to just drop the parentheses in the first part, this binomial here, with 7 plus 3i. Then distribute the negative. Negative 1 times 5, negative 5. Negative 1 times 6i, negative 6i. Parentheses are gone. Combine my like terms. 7 minus 5 is 2. 3i minus 6i is negative 3i. And it looks like I'm done with that one. Okay, pretty easy. Like I said, it's like doing the polynomials. Okay, how about C now? Again, observing, I've got subtraction here. So that means I've got to change my signs or distribute the negative 1. I'll say it that way. The beginning part is nothing happening, so I'm just dropping the parentheses, and I got 5 minus 2i. Now I'm going to distribute the negative 1, so I'm going to have negative 9. Negative 1 times negative 4 is positive 4i. Combine my like terms. 5 minus 9 is negative 4. And negative 2 plus 4i, negative 2i plus 4i is positive 2i. And that is my solution for letter C in complex form. Here for objective E now, we're going to learn to multiply complex numbers. Okay, that's our objective. And notice here they take the form of two binomials. So what are you going to do with this? You got it. We're going to FOIL these two guys. And that's what you do when you're multiplying these complex numbers, when they're in two binomial form like this. Okay, so let's see what happens though when we're multiplying imaginary numbers, complex numbers. All right, so let's FOIL this. So this is going to give me 3 times 2 is 6. Here's first. Outside is 3 times 5i, which is positive 15i. Inside is negative 8i. And last is going to be negative 4i times 5i is negative 20i squared. Okay, so I can address this now, this part here. Notice I have I squared, and I squared is -1. So I could really break this down to be -20 times -1. And -20 times -1 is +20. Okay. So now I'm going to add that 20 to my remaining figures to the left. So that means I'm going to have 6, 15 minus 8, these are like terms, is going to be +7i, and then this 20 now, and it's +20. Now I can add the 6 and the 20 together to give me 26 plus 7i. And now it's been multiplied, and that is my answer for that problem. So you're going to have a change of your signs when you have an I squared at the end when you're foiling, or whenever you multiply two i's together. All right, let's try another one. Okay, let's distribute. 2i times 4 is 8i. 2i times -6i, well, that's going to be -12i squared. And again, here that I squared is -1. So how about 8i minus 12 times -1? Then I'm going to end up having 8i plus 12. Now, written it out this way, it's backwards from the complex standard form, so I'm just going to flip them around. So this answer would change to be in the right form by writing it as 12 plus 8i. And remember what that form was. Standard form is a plus bi. And that's a fit, and that works. So that's example 7. How about example 8 while I have you here? I've got 3 plus 5i, and I'm going to square it. Okay, two ways of doing it now because I've got a binomial squared. I can do the shortcut way. And if I did the shortcut way, let's do it now. What is it I do? I square the first term, this 3, square it, and that'll give me 9. I multiply the 3 components that I see in the problem. That's the only numbers you see, but you multiply them together. So this is a positive, so I got 3 times 5, which is 15i, times 2, which is positive 30i. And then I'm going to take the 5i, the last term, and square that. So that means I'm going to take 5i and square it. And that's going to give me 25i squared. We know that I squared is -1 times 25. So this last part is going to end up being -25 minus 25. Add my like terms together, I get -16 plus 30i. And that's how we roll with that example. What example is that? Example 8. All right, that's the shortcut way. If not using the shortcut way, you could always take that 3 plus 5i squared and then rewrite it to be 3 plus 5i, what am I going to say? Times 3 plus 5i. And then you can go ahead and FOIL that. And you can try foiling it if you like and see if you come up with that answer. All right, how about example 9? I've got another couple binomials that we're multiplying together. So again, we can just FOIL that. This is the product of the sum and difference of the same two terms. So there's a shortcut to this too, but let's not worry about it. Let's just FOIL it. So here I got 2 times 2 is 4. 2 times 3i is positive 6i. Negative 3 times 2 is negative 6i. And then negative 3i times 3i is negative 9i squared. And there's that I squared again. So you know that's going to be minus 9 times negative 1. And that's going to change to positive 9. So I'm going to write this as 4 plus 6 minus 6. These cancel out. And then I'm going to have positive 9. And 4 plus 9 will give you the 13. So that's what this ends up being. A little bit different of an answer than what we're accustomed to when we are using variables. But now we're using I, which forms into a number when you square it. Okay, so that was the last one of those examples. All right, ladies and gentlemen, we've on to objective F, which is division with complex numbers. Okay, division with complex number. Now this is going to take on the like of when we were working with radicals in the denominator. And remember, if I had something like, I don't know, 3 over radical 5, and what's the rule? We had to, we can't have a radical in the denominator, so we have to do what's called multiply by its conjugate. Okay, and the conjugate here of square root of 5 would be another square root of 5. So I'm not doing the conjugate. I'm just multiplying by another square root of 5 for the purpose of getting the radical out of the denominator. Okay, so we did something like this. However, when we went to make this as a binomial, I remember one problem we had 3 square root of 5 maybe plus 3. And then what it is we had to do was multiply by the conjugate. Now the conjugate was the square root of 5 minus 3. And then when you multiply this out, something real nice happened, and so will happen when we're using complex numbers as well. And remember, top and bottom. I'm not being real thorough here, just to give you the idea of what we did, especially with the denominator. I'm multiplying by the conjugate. So we want to know that for when we're using it with imaginary numbers. So, without further ado, let me get this example 10 up, where it is 2 plus I divided by 3 minus 2I. And so what I want to do is multiply the denominator by its conjugate. And that means I'm going to multiply 3 plus 2I, top and bottom. Fair enough? Conjugate. And something nice happens when I do this in the denominator. But first, let's take care of the numerator. All right, and I'll write it underneath it down here. So here I've got 2 times 3 is 6. 2 times 2i is plus 4i. I times 3 is positive 3i. And I times 2i is positive 2i squared. Okay. I can make my notations here to say this is negative 1 times 2, which is negative 2. All right, so when I combine this portion here now, I just made this change of 2 times I squared to be negative 2. I'm going to have 6 minus 2 is 4, plus 4i and 3i is 7i. All right, so that's my numerator. My denominator now is going to be the conjugate of each other, and I'm going to FOIL that. So this is going to be 3 times 3, which is 9. I'll do my work out here. 3 times 2i is 6i. Negative 2i times 3 is negative 6i. And then negative 2i times 2i is going to be negative 4i squared. And there it is again, that I squared, which is negative 1 times the negative 4, which makes it positive 4. So I'm going to have 9 plus 6i minus 6i cancel each other out, plus 4. And 9 plus 4 is 13. And again, that's my denominator, 13. Okay, I don't want to leave it this way. I'm not sure if the computer will take that as your answer, but the more proper way of writing this would be in the a plus bi form. So I'm going to have, if I split the 13 with the 4, so that'd be 4 over 13 plus 7i over 13. And now this is the proper form. This is a, which is 4 over 13, b, which is 7 over 13, times the I. So this is the proper form of the answer you'll get. Okay, we did the conjugate of the denominator because it's a binomial. Okay, so now when we're looking at a problem here in example 11, let's say we have 7 minus 4i, and it's divided by I. All right, so now I can take this and I'm going to multiply top and bottom by its conjugate. Okay, so I'm going to multiply this by negative I, top and bottom, which was different than with a single radical. We just multiplied by another radical of the same number. But now with imaginary numbers, I'm going to multiply by its conjugate. All right, so what do I get when I do this? I'm going to get my numerator here is going to be negative I times 7, which is negative 7i, and then negative I times negative 4i is going to be positive 4i squared. And there's that I squared again, which is negative 1. Cross that off, put negative 1. Negative 1 times 4 is negative 4. So this denominator or numerator is going to be negative 7i, and then what I say that'll be? Minus 4. I want to flip it around to be in the right form of a plus bi, so we'll write this as negative 4 minus 7i. Okay, and then what's my denominator going to be? Well, I got I times negative I, which is negative I squared. But I squared is negative, so how about if I write negative I squared to be negative 1, which equals positive 1. So this is all over 1. And I don't need the 1 then, since it's in the denominator. And so I'll just say my answer is going to be this guy in the box up top, the numerator only. Okay, so remember that, the conjugate when we're doing complex numbers, similar to rationalizing the denominator when we have radicals in. All right, that looks like it's it for example 11. Let's see, that should be page 570, and it is. So that's the lesson for this section of 6.6. So enjoy your day today. Again, happy Easter, and I look forward to hearing from some of you. Any questions, concerns, send me a note in Remind or our Hawkmail through XYZ Homework too. I'll check them all the time, and I'm looking. So thank you again. We'll talk to you soon. Goodbye.